According to the National Electrical Code Section 240.86b, series ratings are not permitted in scenarios where motors are connected on the load side of a higher rated of a current protective device and simultaneously on the line side of a lower rated device when the sum of the motor full load currents exceeds 1% of the interrupting rating of the low rated circuit breaker. This requirement is crucial for ensuring electrical safety and preventing catastrophic equipment failures under fault conditions. When assessing an electrical system's compliance with this code provision, it is imperative to meticulously calculate the total motor full load current and compare it against the interrupting rating of the lowest rated circuit breaker in the series combination. To accurately determine if the motor load surpasses the permissible threshold for series ratings, a straightforward calculation is performed. Firstly, the sum of all motor full load currents is determined, which is the combined current drawn by all motors in the circuit under their rated full load operating conditions. Secondly, this total motor full load current is then compared against 1% of the interrupting rating of the lower rated circuit breaker. If the total motor full load current exceeds this 1% threshold, then series ratings cannot be applied, and the low rated device must possess an interrupting rating sufficient to handle the available fault current at its terminals. In one specific scenario, a main distribution board with a 65,000 amps interrupting capacity feeds a 200 horsepower motor with a full load amperage of 240 amps, a 250 horsepower motor with a full load amperage of 302 amps, and a motor control center section with a total motor load of 437 amps. Variable frequency drives control the two larger motors, and these drives are fed directly from the main distribution board but are only rated for 18,000 amps interrupting capacity. The available fault current at the variable frequency drives is measured to be 23,000 amps. To ascertain compliance with NEC 240.86b, firstly, the total motor full load current must be calculated. This is achieved by summing the individual full load currents of all motors, resulting in a total of 240 amps plus 302 amps plus 437 amps, which equals 979 amps. Secondly, the 1% threshold of the lower rated device must be calculated. In this case, the variable frequency drives are the lower rated devices with an interrupting rating of 18,000 amps. Therefore, 1% of 18,000 amps is 180 amps. When comparing the total motor full load current of 979 amps against the 1% threshold of 180 amps, it is evident that the motor load significantly exceeds the permissible limit. Since 979 amps is considerably greater than 180 amps, series ratings cannot be utilized to validate the 18,000 amps interrupting capacity of the variable frequency drives. Even if the available fault current at the variable frequency drives is 23,000 amps, and series ratings are deemed inapplicable, the variable frequency drives must be fully rated to withstand the available fault current. This necessitates the installation of variable frequency drives with a minimum interrupting rating of 23,000 amps. This ensures that the variable frequency drives can safely interrupt fault currents without experiencing catastrophic failure, thereby safeguarding personnel and equipment. In situations where variable frequency drives are employed in motor control applications, meticulous attention must be paid to their interrupting ratings. Variable frequency drives are electronic devices used to control the speed of alternating current motors by varying the frequency and voltage supplied to the motor. The interrupting rating of a variable frequency drive denotes the maximum fault current that the device can safely interrupt without sustaining damage or posing a safety hazard. When selecting variable frequency drives, it is paramount to ensure that their interrupting ratings meet or exceed the available fault current to their installation location. The available fault current represents the magnitude of current that would flow in the event of a short circuit or other electrical fault. If a variable frequency drive is installed in a location where the available fault current surpasses its interrupting rating, the drive may fail catastrophically during a fault event. This failure can result in severe equipment damage, electrical shock hazards, and even fire. Consequently, it is imperative to conduct a thorough fault current study to determine the available fault current at each point in the electrical system where variable frequency drives are to be installed. This study should consider all potential sources of fault current, including utility power, generators, and transformers. Once the available fault current is determined, variable frequency drives with appropriate interrupting ratings can be selected to ensure safe and reliable operation. The selection of variable frequency drives with adequate interrupting ratings is not merely a matter of code compliance, it is a fundamental aspect of electrical safety. By adhering to the requirements of NEC 240.86b and ensuring that variable frequency drives are properly rated for the available fault current, electrical engineers and technicians can mitigate the risks associated with electrical faults and create a safer working environment. Furthermore, the appropriate application of overcurrent protective devices, such as circuit breakers and fuses, is essential for safeguarding electrical systems and equipment. These devices are designed to automatically interrupt the flow of current in the event of an overcurrent condition, such as a short circuit or overload. Overcurrent protective devices must be carefully selected and coordinated to ensure that they operate correctly and effectively. The interrupting rating of an overcurrent protective device is the maximum fault current that the device can safely interrupt without sustaining damage or posing a safety hazard. When selecting overcurrent protective devices, it is crucial to ensure that their interrupting ratings meet or exceed the available fault current at their installation location. In addition to interrupting rating, other factors to consider when selecting overcurrent protective devices include their current rating, voltage rating, and time current characteristics. The current rating of an overcurrent protective device is the maximum continuous current that the device can carry without tripping. The voltage rating is the maximum voltage that the device can safely interrupt. The time current characteristics of an overcurrent protective device define the relationship between the magnitude of overcurrent and the time it takes for the device to trip. Proper coordination of overcurrent protective devices is essential for ensuring that the device closest to the fault will trip first, minimizing the extent of the outage and preventing damage to upstream equipment. Coordination studies are typically performed to determine the appropriate settings for overcurrent protective devices in an electrical system. These studies involve analyzing the time current characteristics of each device and ensuring that they are properly coordinated with each other. In conclusion, the selection and application of variable frequency drives and overcurrent protective devices require careful consideration of interrupting ratings, available fault current, and coordination. By adhering to the requirements of the National Electrical Code and employing sound engineering practices, electrical professionals can ensure the safety and reliability of electrical systems. The National Electrical Code, or NEC, serves as the cornerstone for electrical safety in the United States. It provides a comprehensive set of standards and guidelines for the safe installation and maintenance of electrical systems. Compliance with the NEC is not merely a matter of adhering to regulations, it is a fundamental obligation to protect people and property from the hazards associated with electricity. The NEC is developed and updated by the National Fire Protection Association, or NFPA, a non-profit organization dedicated to reducing the risk of fire and other hazards. The NEC is revised every 3 years to incorporate new technologies, address emerging safety concerns, and improve the clarity and enforceability of its provisions. The NEC covers a wide range of electrical topics, including wiring methods, overcurrent protection, grounding, equipment installation, and special occupancies. It provides detailed requirements for the selection, installation, and maintenance of electrical equipment to ensure that it operates safely and reliably. The NEC is not a design manual, it does not provide specific instructions on how to design an electrical system. Rather, it sets forth minimum safety requirements that must be met in all electrical installations. Electrical engineers and contractors are responsible for designing electrical systems that comply with the NEC and meet the specific needs of the application. The NEC is enforced by local jurisdictions, such as cities, counties, and states. These jurisdictions typically adopt the NEC as part of their building codes and employ electrical inspectors to ensure that electrical installations comply with its requirements. Electrical inspectors review plans, conduct site inspections, and issue permits to ensure that electrical work is performed safely and in accordance with the NEC. Compliance with the NEC is essential for obtaining insurance coverage for electrical systems. Insurance companies typically require that electrical systems be installed and maintained in accordance with the NEC as a condition of coverage. Failure to comply with the NEC can result in denial of insurance claims in the event of an electrical fire or other incident. The NEC is not a static document, it is constantly evolving to keep pace with technological advancements and address emerging safety concerns. Electrical professionals must stay up to date with the latest changes to the NEC to ensure that their work complies with current requirements. Continuing education courses, industry publications, and online resources are available to help electrical professionals stay informed about the NEC. The NEC is an indispensable tool for electrical safety. It provides a framework for the safe installation and maintenance of electrical systems, protecting people and property from the hazards associated with electricity. By adhering to the requirements of the NEC, electrical professionals can contribute to a safer and more reliable electrical infrastructure. In the context of motor control centers, understanding the nuances of short-circuit current ratings and how they interact with the NEC is crucial. A motor control center, or MCC, is an assembly of motor starters, overload relays, circuit breakers, and other control devices used to control and protect electric motors. MCC are commonly used in industrial and commercial facilities to control a large number of motors from a central location. The short-circuit current rating, or SCCR, of an MCC is the maximum fault current that the MCC can safely withstand without sustaining damage or posing a safety hazard. The SCCR of an MCC is determined by the weakest link in the assembly, which is typically the component with the lowest SCCR. When selecting an MCC, it is essential to ensure that its SCCR meets or exceeds the available fault current at its installation location. The available fault current represents the magnitude of current that would flow in the event of a short circuit or other electrical fault. If an MCC is installed in a location where the available fault current surpasses its SCCR, the MCC may fail catastrophically during a fault event. This failure can result in severe equipment damage, electrical shock hazards, and even fire. Consequently, it is imperative to conduct a thorough fault current study to determine the available fault current at each point in the electrical system where MCC are to be installed. This study should consider all potential sources of fault current, including utility power, generators, and transformers. Once the available fault current is determined, MCC with appropriate SCCRs can be selected to ensure safe and reliable operation. The NEC provides specific requirements for the SCCR of MCC. Section 408.6 of the NEC requires that MCC be marked with their SCCR and that the SCCR be sufficient to withstand the available fault current at the terminals. The NEC also provides guidelines for determining the SCCR of MCC, including the use of component short-circuit ratings and series combination ratings. Component short-circuit ratings are the SCCRs of individual components within the MCC, such as circuit breakers and motor starters. Series combination ratings are the SCCRs of combinations of components that have been tested together and found to have a higher SCCR than the individual components. When determining the SCCR of an MCC, it is important to consider all potential sources of fault current and to use the most conservative approach. If there is any doubt about the SCCR of an MCC, it is best to consult with the manufacturer or a qualified electrical engineer. In addition to selecting MCC with appropriate SCCRs, it is also important to properly install and maintain them. MCC should be installed in accordance with the manufacturer's instructions and the requirements of the NEC. Regular maintenance should be performed to ensure that all components are in good working order and that there are no signs of damage or deterioration. The selection, installation, and maintenance of MCC require careful attention to short-circuit current ratings and compliance with the NEC. By following these guidelines, electrical professionals can ensure the safety and reliability of MCC and protect people and property from the hazards associated with electrical faults. The concept of series ratings in electrical systems warrants careful consideration, particularly in the context of motor control circuits. Series ratings refer to the practice of using overcurrent protective devices with different interrupting ratings in series, where the upstream device has a higher interrupting rating than the downstream device. The intent of series ratings is to allow the use of lower-cost, lower interrupting rating devices downstream, while still providing adequate protection against fault currents. However, the application of series ratings is subject to strict limitations and requirements in the National Electrical Code. NEC Section 240.86 outlines the conditions under which series ratings are permitted. One of the key requirements is that the series combination must be tested and listed as a series-rated system by a qualified testing laboratory. This testing ensures that the upstream and downstream devices will coordinate properly during a fault event and that the downstream device will not be damaged or fail catastrophically. Another important limitation on series ratings is that they are not permitted in certain applications where there is a high risk of motor contribution to fault currents. Motor contribution refers to the phenomenon where motors connected to the electrical system can continue to supply current to a fault even after the upstream overcurrent protective device has opened. This motor contribution can increase the magnitude and duration of the fault current, potentially exceeding the interrupting rating of the downstream device. NEC 240.86b specifically prohibits the use of series ratings where motors are connected on the load side of the higher rated overcurrent device and on the line side of the lower rated device, and the sum of the motor full load currents exceeds 1% of the interrupting rating of the lower rated circuit breaker. This provision is designed to prevent the use of series ratings in situations where motor contribution could compromise the safety of the electrical system. When evaluating the applicability of series ratings in a motor control circuit, it is essential to carefully consider the potential for motor contribution and to ensure that the requirements of NEC 240.86 are met. If there is any doubt about the suitability of series ratings, it is best to consult with a qualified electrical engineer. In situations where series ratings are not permitted, it is necessary to use overcurrent protective devices with interrupting ratings that are sufficient to withstand the available fault current at their terminals. This may require the use of higher cost, higher interrupting rating devices, but it is essential for ensuring the safety and reliability of the electrical system. The application of variable frequency drives in motor control systems introduces additional considerations related to short circuit protection. Variable frequency drives, or variable frequency drives, are electronic devices used to control the speed of alternating current motors by varying the frequency and voltage supplied to the motor. Variable frequency drives can offer significant energy savings and process control benefits, but they also require careful attention to short-circuit protection. Variable frequency drives typically have lower short-circuit withstand ratings than traditional motor starters. This is because variable frequency drives contain sensitive electronic components that can be damaged by high fault currents. Therefore, it is essential to ensure that variable frequency drives are properly protected against short circuits. The National Electrical Code provides specific requirements for the short-circuit protection of variable frequency drives. NEC Section 430.130 requires that variable frequency drives be protected by overcurrent protective devices that are sized and coordinated to protect the drive against short circuits and overloads. The overcurrent protective devices must be selected to have an interrupting rating that is sufficient to withstand the available fault current at the variable frequency drive terminals. In addition to overcurrent protection, variable frequency drives may also require additional protection against other types of faults, such as ground faults and voltage surges. Ground fault protection is typically provided by ground fault relays which detect and interrupt ground faults. Voltage surge protection is typically provided by surge protective devices, which protect the variable frequency drive against voltage transients caused by lightning or switching surges. When selecting overcurrent protective devices for variable frequency drives, it is important to consider the drive short circuit withstand rating, the available fault current, and the coordination requirements of the electrical system. The overcurrent protective devices should be selected to provide adequate protection against short circuits without causing nuisance tripping. It is also important to ensure that the overcurrent protective devices are properly coordinated with other protective devices in the electrical system to minimize the extent of any outages. The short-circuit protection of variable frequency drives is a critical aspect of electrical system design. By following the requirements of the National Electrical Code and employing sound engineering practices, electrical professionals can ensure the safe and reliable operation of variable frequency drives.